Okay, so this video we're going to discuss the next topic in chapter 6, which is the method of joints. So for truss, we need to know the force in each members. That is ultimately the goal. Okay, so for example, we have this truss. It has 3 members. Okay, AB, BC, and CA. And there's one external force acting on it. So we wish to know what are the forces developed in each of these members because of this external load, and of course due to this support. Okay, remember this is chapter 5 all over again. You have this support. So forces in the members are internal forces. So there are forces that you don't see. Okay, and there are also external forces. So for this, you can apply the equations of equilibrium. What are external forces? Of course, the one that is given here, and also the support reactions. So it's important that we note that the force system acting on each joint is coplanar and concurrent. Okay, so that means all these members are concurrent, and they're acting only on the 2D plane. And of course, the force equilibrium equations or the force balance must be satisfied. So we are actually applying what you have learned way from chapter 2 and 3 to this chapter. Okay, so let's first take this example. At point B or at joint B, if we were to construct the free body diagram at joint B, this is what you're going to get. We have the external force 500 newtons, and we have tension or compression forces in members BA and BC. So how do you determine whether it's tension or compression? Okay, that is actually initially an assumption, but we can make a very sound assumption that is almost guaranteed to be correct. Alright, so I will explain that as we go along. And this is actually how the free body diagram will look like for joint B. So if you remember your test, most of you did not do the free body diagram. So this is how it should actually be done. Okay, when you want to study the forces in any member in a cable or whatever it is, you must construct the free body diagram. Okay, so how to do this in the structural analysis? So first, draw FBD with at least one known and two unknown forces. Okay, it makes sense to start with one known forces, because with that known force you can find the other two unknowns. Okay, if you start with all unknown forces, then you're not going to solve anything. So find the external reactions at the truss support. So we also need to include the reaction forces. Okay, this is chapter 5. And then we determine the correct sense of the member. This is either tension or compression. Okay, this is what I told you that I will explain, the assumption. And then we orient our x and y axis. It doesn't have to be the common x and y axis. And then we apply the force balance equations. Okay, use known force to analyze the unknown force, way from step 1. Okay, we start with the FBD where we have one known force. So ultimately we want to determine the unknown forces. Okay, so let's do this example. Determine the force in each member of the truss and indicate whether they are members in tension or compression. So first, let's analyze the diagram. At joint B, we have two unknown member forces. Okay, and where they are coming from is in this member, alright, and in this member. I'm not going to write the direction yet. Alright, so it could either be going this way or going this way. We'll figure it out later. Now, at joint C, we have unknown reaction force. Okay, if you recall, this is a rocker, therefore a rocker will have one perpendicular support. Okay, and we also have, of course, the force in the members. So the force in the members, this force and this force are one and the same. Okay, they are acting in the opposite direction. It depends on the direction of one, and then you can determine the direction of the other one, but they are actually the same force. So FBC equals to FCB. Okay, because there's only one force in each member. Why are we getting two different forces? Because we are looking at them by each joint. Okay, so we have one unknown reaction force at C because of the rocker, and two unknown member forces in member BC and member AC. And lastly, in joint A, okay, you have two unknown member forces, which are of course this AC and AB. And we have, because of the pin support, if you recall, the pin support will result in two unknown reactions, here and here, X and Y direction. Okay, so from this you can draw the FBD and start to figure out. So we start with joint B, because remember, to start you have to choose the joint that has one known information and two unknown information. So the only known information that we have is joint B. If you compare at joint C, you have three unknowns. At joint A, you have four unknowns. So B is the only place to. Okay, so what we do first, after you've selected the point or the joint from your initial analysis, is to draw the FBD. So how do we draw the FBD for joint B? So just draw the point, and then we know that it's 500 newtons, and then we know that there are two member forces. The question is, how do you assume the direction of the member forces? Okay, that's actually quite simple. So you look at, you know that ultimately you want to do the force balance, meaning that you want to do Fx equals 0, Fy equals 0. So just looking at point B and this 500 Newton load, how do you balance this 500 Newton? Of course, by having a force to the left, right? Just to counter this. And the only way for you to have this force to the left is if FBC is acting upwards like this, up and leftwards. The alternative is to go down here, which of course it will still go to the right, and you will not balance this 500 Newton. So the only way to balance is to have force going to the left. That is FBC going this way. Alright, now FBA is the same. So this is suddenly now you have a force going upwards. Okay, you have a force going upwards. Now the left is already balanced by this. Now it's going upwards. So the only way to balance that is to have a force going downwards. So FBA is downwards because we need to balance the forces. Okay, now you've figured out the free body diagram. This is how it looks like. You can calculate. Okay, so summation of F in X direction equals to 0. We have 500 Newton, positive because it's going to the right. And then we have FBC sine 45, negative because it's going to the left, equals 0. So FBC is 707.1 Newton in compression. Okay, so if it's pushing into the joint, then it's considered as a compression. Now in Fy equals to 0, you do the same thing now that you know FBC. So FBC cos 45 going upwards, that's why it's positive, minus FBA, this is going downwards, that's why it's negative, equals to 0. Then you can find FBA. Now FBA is moving away from the joint, therefore it's in tension. See, we have two member forces and we have one support. Okay, so first from B, if you recall, this was going this way. Okay, so this one has to act this way because they balance each other out. Okay, and of course we know that in a rocker the force is perpendicular, is upwards, because to balance this force, this is going downwards, this has to go upwards. And here in AC, because we have one member, force going to the right, so this has to go to the left. Okay, then you have this FBD. So from this FBD you can pause to work out the calculation, and you will find FCA and CY, or FC, whichever you want to call it. Okay, so with this we can proceed with joint A. Joint A, initially we had 4 unknowns, but now FBA and FCA are known. And the direction, of course, you still need to draw the FBD. Look at this diagram. This is going to the left, so therefore it's going to the right. This is going upwards. Okay, this is from earlier, from the analysis of joint B. So therefore the support has to balance these two. So AY has to be downwards, AX has to be going to the left. Okay, just like as it's shown here. And then again you can pause and work out to calculate the two unknowns, AX and AY. Okay, so the answer can be summarized here in this picture. So FBD of each pin shows the effect of all the connected members and external forces applied to the pin. And FBD of each member shows only the effect of the end pins on the member. So what you have to realize here, how did this force become a compression force in member BC? Okay, when we studied the joint, so let's focus on this joint. Okay, when we studied this joint, we have separated the member away from the joint. So you have this pulling, and actually here, why it's compression? Because you have at the member's end, you have the force that is reacting to this. Okay, so these two forces are reacting to each other. And at the other end, you have the force to balance it out. So that's why even though it looks like the force is pulling into the joint, looks like it's stretching, but actually it is in compression. Because when we study the member only, you will get these forces, okay, which are compressing the member. Okay, so the answer is you have the forces, okay, in BC, and this is in AC, and this is in AB, and they are in compression for BC, tension for AC, tension for AB. Of course, you don't have to draw this diagram as the final answer. You can just write something like this: FBC equals to 707.1 newtons compression. Okay, just like how it was written in previous slides. Okay, so we'll be discussing maybe 1 or 2 questions based on what you've learned in this video.